when it comes to heat transfer problem, so Q is replaced by T. So we have thermal conductivity matrix. Already you are familiar with the thermal conductivity of the different material. The thermal conductivity of the copper is more compared to steel, etc. Even thermal conductivity of the aluminum is more compared to steel or some other material. That's why this even in the case of heat exchangers, etc., they use the copper material, especially for radiator, etc. The copper based alloy materials are used because thermal conductivity of those materials are very higher compared to steel or some other material. So when you come to heat transfer analysis, so you have equilibrium equation. The original equilibrium equation is KQ is equal to force. But when it comes to the heat transfer problem, so Q is replaced by T. So where T is the field variable, when it comes to heat transfer, field variable is temperature. So there is no stiffness. The concept of stiffness in the case of heat transfer problem. So instead of stiffness, 1 minute. So there is no concept of K or stiffness in the case of heat transfer problems. So this complete stiffness matrix is replaced by thermal conductivity matrix. So most of the conduction problems you are familiar with the thermal conductivity K, and some cases H. The H also you are using. H matrix also there. One more is K matrix, thermal conductivity matrix. So where KT is equal to Q. On the right hand side, we have force vector. The force vector is when it comes to heat transfer problem. So where force is replaced by Q or heat transfer rate. That means when you come to heat transfer, we have equilibrium equation. So it is not the regular structural equilibrium equation. It is thermal equilibrium equation. Thermal equilibrium equation is KT is equal to Q. So where K is the thermal conductivity matrix and T is the temperature vector T1, T2, T3, etc. On the right hand side, we have the Q. So most of the time, it is a lowercase letter Q. So there are two Qs you are using. One is uppercase letter Q, that is heat transfer, and one more is lowercase letter Q, the heat transfer per unit area. So there are two terms used in heat transfer. So one is total heat transfer. The total heat transfer is referred by capital letter Q. And one more term you are used is heat transfer rate or heat flux. Normally you are referring to heat flux. The heat flux is nothing but the heat transfer per unit area that you should be able to differentiate when you design some equations. So now complete heat transfer, why I am revising this is complete heat transfer derivation. Already I have shared the notes, the PPT, this PDF file of this notes in WhatsApp group. Most probably today or tomorrow I'll share the same thing in the Google Classroom. Please refer these notes, especially for module 3 and module 4. So most of the local books it's not given clearly. I suggest you to refer my notes. Complete theory and derivation for heat transfer module. It is around 45 to 50 page. So it is already circulated in your WhatsApp group, and shortly I'll put it in the Google Classroom also. So time being, you can read those notes in your mobile or laptop. So once the situation comes normal, so I suggest you to take the printout, and in the printout only, hard copy of the notes only you study. Only if you better to have one highlighter. If there is some important formulas or important steps, you highlight it. That is the best way of learning for the scoring purpose. There are two ways of learning, one for knowledge purpose and one more for getting good marks. For university examination purpose, better to have, especially problem like the subject like finite element method, better to have hard copy of the notes. Time being, you can refer the soft copy of the notes. But once the situation comes to normal, better to take the printout and keep it with you. Now I'll go fastly. I'll go for revision of this. Now you have to remember in finite element analysis. So even though you are saying the bar element, so as per your packages are considered, your packages are not developed for a particular application. In general, you have to remember whatever may be the finite element packages is not you developed for the particular application or particular boundary condition. Even though we have a physical structure or mechanical structure is like this, still you are putting u1 is equal, the displacement at node 1 is equal to u1, displacement at node 2 is equal to u2. In some cases, displacement at node 1 may be 0. In some cases, displacement at node 2 may be 0. So when come to the heat transfer analysis, similar type of element, so where u is replaced by temperatures. At node 1, the temperature is T1. At node 2, the temperature is T2. I think you can come through your mail ID. Don't join through the group, this link. I have to, for each and everything, I have to put accept, accept, accept. Now, even in the heat transfer problems also, same type of element. We have two noded heat transfer element where temperature is at node 1 is T1, at temperature at node 2 is T2. At one side, at T1 maybe T0. It may be exposed to directly to the some heating element, or if it is an internal combustion engine, what is the temperature inside the engine, the inside surface of the engine or inside surface of the let it be the cylinder that will be referred as T0. So outside temperature, outside surface temperature of the engine may be T infinity. That's the only different. So we have mechanical structure. So mechanical structure we have referred by the finite element model. We have, it is like a bar, simple bar element only. At node 1 displacement is u1, at node 2 displacement is u2. So now, so we have the potential energy functional. You are saying the function means potential energy is a function of strain energy. We can see here the potential energy is a function of strain energy. It is also a function of the work potential. So work potential is nothing but a work done due to the application of the load. I have given the same example. So we are giving this, imagine we have the spring of so let it be 100 mm length. You are compressing the spring. So when it is compressed, so imagine it is compressed by 50%. So we are applying load of 100 Newton. So to 100 Newton of load is moved by 50 mm distance. So then 100 into 50, that gives the work done. So imagine you are applied around 100 kilowatt of power, and there will be 1000 watt of power for applying the load. So only around 40% of the energy is spent for the work done. The remaining amount of energy is stored in the spring, that is referred as a strain energy. Same concept is used in our the heat transfer analysis also. So when body is at room temperature, it has some energy. So when temperature rises to around 200 degrees Celsius or 300 degrees Celsius, the temperature is increased. Because of the increase in temperature, heat energy is also increased. So where instead of talking strain energy, you are talking about the heat energy. So now whatever, whether it is a strain energy or heat energy, so every energy is a functional. So it depending upon many parameters. If it's considered, imagine you have the red hot rod. So even you are familiar with forging also. In the case of forging, so in the case of forging, so when temperature is at room temperature, so then you are heating the material. So before heating the material, so it has some amount of energy, because when temperature is around 25 degree or 30 degrees Celsius, still it has some heat energy. Any body or any material having temperature more than the 0 Kelvin has energy as per your thermodynamics. In the similar way, so when this forging rod is at room temperature, it has some energy. So when it is heated to red hot condition, normally it is around 200 degrees Celsius or 300 to 400 degrees Celsius, the energy content of the system will be increased. Now, in the case of spring, that is a concern with heat energy. So at room temperature, the forging rod is having lower energy. So when temperature is increased to around 500 degrees Celsius, the energy content will be increases. So your energy content is a function of many parameters. So one is the temperature of the body, and second one is the thermal conductivity of the heat content. Normally referred as heat capacity, the heat capacity of the body, the heat capacity of the body. Hence, your energy is a function of one is temperature, and what is the second one is heat capacity. So heat capacity is nothing but you are saying Cp. So heat capacity is nothing but how much amount of energy it can carry for 1 kg of the fluid or 1 kg of the mass. So that means it is a function. It is a your energy, whether it is a mechanical energy or deformation energy or thermal energy. It is a function of many parameter. Hence, you are using the term functional. The function is nothing but a function of the function. That means we have potential energy, or potential energy is nothing but total energy of the system. It is a function of strain energy, and it is also a function of work potential. It's also a function of work potential. So now strain energy is, we have potential energy. It's a function of strain energy. The strain energy is in turn is a function of the stresses as well as strain. Hence, it is because we have potential energy. So potential energy is a function of strain energy and work potential. Now, when you come to strain energy, the strain energy stored in the body is depending upon the deformation. So hence it is a functional or function of the function is referred as a functional. If you go for typical definition of the mathematics, hence it is referred as a functional approach. So most of the heat transfer problems are solved by functional approach. So instead of strain energy, you are going for the heat energy. We have the then work potential. Work potential is nothing but work done. It is force into distance. We have the equation for strain energy. The strain energy is nothing but area below stress strain curve. So area below the stress strain curve is half into sigma into epsilon. So then, so we can get the equation for epsilon. Epsilon in general, in you are referring epsilon is equal to delta L by L. So that when you come to finite element analysis, the displacement is given by U and original length is given by L. But you are considering a very small elemental length. For small elemental length, the displacement is du, del u, and the original length of the element is given by dx. Finally, we get the strain energy. Epsilon is replaced by, strictly speaking, the definition of the strain or equation for the strain is given by del u by del x, but initial level in mechanics of material, etc., you are referring it as delta L by L. But strictly speaking, the formula for strain is del u by del x, del v by del y, and del w by del z. If you substitute all those things, you get one equation. This is the strain energy. So the strain energy is again integral function. So it is originally it is a volume integral. If it is three-dimensional analysis, then it is a volume integral. But bar is comes under one-dimensional. The loading is predominant in only one direction. In the similar way, you have one-dimensional heat conduction, two-dimensional heat conduction, and three-dimensional heat conduction. So in one-dimensional heat conduction, the heat flow, the major heat flow is in only one direction, in the x direction. So instead of writing del u by del x, there you are writing del t by del x, where the temperature or field variable is the temperature. So instead of writing, when you come to heat transfer, so you are writing instead of writing del u by del x, this complete heat energy is given by del t by del x. Most of the time in the numerator we have del t by del x. If it is two-dimensional heat transfer, we have del t by del x, and one more term is del t by del y. If it is a three-dimensional heat transfer, del t by del x, del t by del y, del t by del z. If it is three-dimensional, so that the energy equation remains same. So it is an integral equation. If it is one-dimensional heat transfer, it is only single integral 0 to L. So now work done. So work done, you are familiar. Work done is equal to force into distance. So node 1 is moved by a distance u1. The force is at node 1 is u f1. The total work done is f into u1 at node 1. Similarly, for work done, so work done is nothing but you are imagine I am giving the same example so you can understand better. So the original height of the spring is 100 mm. So you are applied around 100,000 Newton of force. So it is compressed to 50 mm. The total distance moved by that particular end of the spring is 50 mm. The force applied is 1000 into 50 gives the total work done. In the similar way, at node 2, the work done is given by F2 into U2. That is nothing but force into, in simple way, F2 is force, U2 is deformation or displacement. If we substitute all those things, we have final equation for potential energy functional. Same equations used even in the case of Rayleigh's method of your first module. So again, Rayleigh's method, you are using the potential energy approach. Even for deriving the equation for stiffness matrix for the truss element also, we are used the same potential energy approach. When you deriving the stiffness matrix for the beam element also, we are used the potential energy approach. So when you're deriving the stiffness matrix for the torsional element also, again you are using the potential energy approach. In simple way, the complete finite element analysis based on energy approach. So in the simple way, energy approach is nothing but system is in equilibrium condition only when the rate of change of energy is zero, or energy is zero, but energy cannot be zero. So thermal energy cannot be zero, because only when you take the material below 0 Kelvin, then only 0 Kelvin, then only energy becomes zero. But in finite element analysis, you are saying that the rate of change of energy is zero, then only system is in the equilibrium condition, or variation of the energy is zero, then only system is in the equilibrium condition. That's why you are studied about the variational calculus. Now we have the potential energy functional pi here. I think PPT is visible now. PPT. Someone can respond. PPT is visible or not?
Yes,
Yes,
sir.
sir.
Yes. So now we have the pi. The pi is nothing but a total energy content of the system. If it is structural mechanics, so your bar, beam, trusses, all will come under the structural mechanics problems. There is a one more heat transfer, fluid dynamics problems, and one more is the heat transfer problem. But as per your 17 scheme is considered, fluid dynamics problems are excluded. In 16 scheme, it was there. Last year batches we had done the finite element analysis for the fluid flow also, but now as per your syllabus, it is not that is removed. They have added some more portion from the vibration analysis. So whatever may be the type of system, so we have the energy. So when the variation of the energy is zero, then only system is in the equilibrium condition. That means we have the energy equation pi. So variation of the energy is nothing but the rate of change of energy. Rate of change of energy is nothing but differentiation of pi with respect to the field variable. The different field variable in the case of structural mechanics is the displacement or deformation. So field variable in the case of the heat transfer is the temperature. When you come to finite element analysis, the heat transfer, so our main objective is to find out the temperature at different nodal point. We have KT is equal to Q. So where K is thermal conductivity matrix, the T is temperature vector. On the right hand side, we have heat flux vector, normal heat force vector or heat flux vector. So where regular force is replaced by heat flux Q. So now we have energy equation. You have to differentiate this energy equation with respect to field variable. The here field variable is you have to remember. So before that, you have to find out the displacement function. There are two nodal conditions. There are two. You already have familiar with this equation. U is equal to A0 plus A1x. There are two nodal conditions at node 1 and node 2. At node 1, so U1 is known. At node 2, U2 is known. By knowing those two nodal conditions, we get two equations. There are two unknowns. U is equal to A0 and A1. By knowing those two equation and two unknowns can be calculated. Finally, we are getting the value of A0 and A1. That I am not going in detail because already you have discussed it in detail. But you have defined the displacement function by using polynomial function. In the similar way, when you come to heat transfer, you are going to define the temperature. You are assuming the temperature function. So instead of here U, there you are writing T is equal to A0 plus A1x. There you are defining the temperature. Finally, you are getting your equation for U, and if you substitute everything, you are getting some equation for equation. The final energy equation. So that is the strain energy stored as the total energy of the system. This last two term is correspond to potential energy, this work done. The first term is correspond to strain energy. So when you come to this total energy, the system is in equilibrium only when total energy of the system is minimum or variation of the energy is minimum. That's why you are using the term the principle of minimum potential energy. So according to the principle of minimum potential energy, the system is in equilibrium. So when the variation of the energy is zero, the variation is nothing but differentiation. We have the final equation, equation number 14. You have to differentiate this equation. Differentiation is nothing but a variation. So variation, rate of change of rate of change of velocity is nothing but acceleration. Rate of change of the speed is nothing but your this velocity. In the similar way, you are considering the rate of change of energy with respect to field variable. So that means there are two field variable here. So one is u1 and one more is u2. So first we have to differentiate with respect to u1. That is nothing but rate of change of energy with respect to u1. So one more is the rate of change of energy with respect to u2. So by knowing those two, so we can get the equation. So once you differentiate with respect to u1, we'll get one equation, equation number 16. If you differentiate with respect to u2, we'll get one more equation, equation number 17. I'm not going in details about mathematical part, already we have discussed. So finally, I want to say that, so by differentiating the potential energy functional with respect to u1, we'll get one set of equation. That equation is equation number 16. So once you differentiate that equation, or so it is nothing but variation of the energy is zero, or differentiation of pi with respect to u2, you get one more set of equation. So now I have written those two set of equation. Already you have derived those two set of equation. I have written one below the other so that you can understand better. We have two equation. Those two equations you are writing in the matrix form. So you can see here. So we have matrix form AEL into U1, we are getting the first term. So minus AEL into U2, you're getting the second term. That's equal to F1, that is third term. So we have equation 16 and 17. Those two equations you are writing in the matrix form. So once you write those equations in the matrix form, so we'll get you have to get it back. So finally we can write Ku is equal to F. This matrix is K. Stiffness matrix for the bar element is equal to U. U is nothing but displacement is equal to F. Same thing can be written as KQ is equal to F. So KQ is equal to F equation you are using for almost 3 to 4 elements. Already you have dealt with 4 elements. One is bar, truss, beam, as well as torsion. So now, so this K matrix is nothing but AE by L. This is a K matrix. We can take out AE by L. So once you take out AE by L, finally you get K of the bar element is AE by L into 1 minus 1 minus 1 1. That equation already we have used. So that means, so we have equilibrium equation. So equilibrium equation is nothing but KQ is equal to F. When you come to heat transfer problem, the K is thermal conductivity problem matrix. Q is replaced by temperature vector. Q is displacement. In the case of structural problems, the Q is displacement. In the case of heat transfer problem, the Q is replaced by the temperature. Q is replaced by T. But finite element package is designed for all problems, whether it's a fluid problem or heat transfer problem or structural problem, whatever it may be, the equilibrium equation remains same. KQ is equal to F. In the similar way, you have to derive the thermal conductivity matrix for the heat transfer element. That's the first part. That this derivation already derived in the previous class. Just I highlight some of the important concepts. So now next part is the application of boundary condition for non-zero boundary condition. So what is, can you give an example for non-zero boundary condition, at least after discussing so much of things? What is meant by non-zero boundary condition? At least one example. You are dealt with heat transfer. You are studying the heat transfer from the last 2 to 3 months. One example with respect to heat transfer where you can give one example where the boundary condition is non-zero. Non-zero is nothing but in most of your bar problem, truss problem, you are saying that Q1 is equal to 0. So once you say Q1 is equal to 0, It is homogeneous boundary condition. You have heard about homogeneous equation and non-homogeneous equation. In the case of homogeneous equation, right side terms are 0. In the case of non-homogeneous equation, on the right side terms are not 0. In the similar way, you have Q1 is equal to 0 when bar is fixed at node 1. Q1 is equal to 0. So once you say Q1 is equal to 0, on the right hand side we have 0. Hence, it is referred as the homogeneous boundary condition or zero boundary condition. The field variable is 0. Displacement is the field variable in the case of ball trusses. Field variable is 0. But when you come to temperature, this heat transfer, can you give an example for non-zero boundary conditions in the case of heat transfer? Heat transfer is your applied boundary conditions, or at certain point we know the temperature. Imagine you have the steel rod is heated, so we can keep some thermocouple at the one end of the rod. You are I think you have conducted some experiment in metrology and measurement lab. At one end of the rod, the temperature is known. Other end of the rod, steel rod, so is exposed to the ambient temperature, that is T at the end, other end, when x is equal to L, the T is equal to T infinity. When x is equal to 0, or where it is where thermocouple is mounted on the other end of the rod, so where temperature is known, temperature is not 0 there. So we cannot say that temperature is 0 Kelvin or 0 degree. Those are the extreme cases. It may happen, but in normal cases, when you come to heat transfer analysis, the temperatures are not 0 like your structural analysis. Most of the structural analysis, when beams are fixed at both the ends, the displacement is 0. When beams are fixed at both the ends, the angular deformation is 0. When bar is fixed at one end, their deformation is 0. But when you come to heat transfer analysis, most of the cases, those boundary conditions will not apply. In such cases, you have to go for same penalty approach as well as elimination approach of handling non-zero boundary conditions. Now, can you give an example where a temperature is known? The heat transfer, what are the boundary conditions? At least one of you can answer, no, at least after studying the heat transfer. So one thing is you require the domain knowledge, not only the finite element knowledge. To go for finite element analysis, you require the domain knowledge. That's why most of the companies, those who want to hire you for analysis purpose, they'll check whether you have the knowledge of mechanics of material, or this even material science, or design one, the basic concept of designs, or theory of elasticity, etc. If you know only that finite element analysis, the subject, or if you know only your ANSYS or Nastran or Abacus, that is not sufficient. Those software can be taught by a company. They can give the training for 1 month or 2 months, or even they may ready to give the training for 3 to 4 months. But fundamental cannot be studied in 1 to 3 months. That fundamental you are studying from what if you fundamental you are studying is, that is you are studied during 4 years, that cannot be learned within 3 to 4 months. Only software you can learn. So now, what is the boundary condition in heat transfer? Very fastly tell me. One boundary condition in the heat transfer. No one is answering. So normally it is referred as specified temperature boundary condition. The specified temperature boundary condition is nothing but the temperature is known at that particular point or that particular surface. So best example is even in our college of foundry and forging lab, the thermocouples, the furnace is there. The thermocouples are mounted on the furnace inside wall. The inside wall temperature is known. That is nothing but T0. That is the one boundary condition. If you consider the outside surface, the steel surface outside where it is exposed to the atmosphere, where temperature is known, that is nothing but a T infinity. As per your heat transfer terminology is considered, it is heat infinity. That is referred as a specified temperature boundary condition, where temperature is known at certain point. When you come to finite element analysis, either temperature is known on the one end of the element, or we may know the temperature at the other end of the element. That is nothing but a specified temperature boundary condition. And one more boundary condition is the PPT is visible now? Yes or no? Yes or no?
Yes, sir. Yes, sir.
Okay, okay. So now that is the one boundary, specified temperature boundary condition, because in complete heat transfer we are dealing with only the equations and integral. Most of the time we are ending with the integral equation or differential equation or integral differential equations. So to understand those derivations, you require some knowledge, basic knowledge of your heat transfer or some fundamental of finite element analysis. That's why I'm explaining these concepts now. If you're explaining your penalty approach and when you're solving the problem, you may have confusion. What penalty approach you have used or what elimination approach you are already used. That is a very simple for the bar trusses, etc. When you come to heat transfer, when you're going for non-zero boundary condition, slightly you have to go for the different methods. So now, why I'm going to discuss about penalty approach of non-zero, because the most of the problems in finite element analysis of the heat transfer problems are dealing with non-zero boundary condition. So when you come to the penalty approach, already you have used the penalty approach. In simple example is forget about this PPT. So we have the imagine we have the fan. Imagine fan is mounted to the roof, because the roof or the steel rods are there with some plastic wire. So once the fan is mounted on the roof by plastic wire, the fan can slightly move down. Let it be around 5 mm or 10 mm. It can slightly move down. So that means fixed end of the fan, even though you are saying that it's a fan is fixed to the floor or the roof, still it can move down by a small amount. That movement is given by A1 here. I'm putting that same diagram in the opposite direction for understand the concept. Imagine where the fan is mounted. You are assuming that where fan is mounted, you are saying it is a node number one. For node number one, your fixed node number one is fixed. So node number one is fixed. Your displacement is 0. But there may be small, if it is mounted, if it is tied fan to the roof by plastic wires, then you cannot say that displacement is 0. There may be small amount of displacement. It is smallly comes down. Comes down by a small amount, that may be 5 mm or 10 mm. Let it be 10 mm for understanding. That 10 mm is nothing but A1. So even though, so you are saying that so it is fixed or supported, still there is a chance of moving by small amount, like a ground. So most of the time ground is fixed, position is fixed. During earthquake, etc., even for especially for the building construction, civil, when you design the civil structure by using the same finite element analysis, they are assuming that ground is fixed or foundation is fixed. But it is not true during the earthquake. During the earthquake, the whole ground or foundation itself is moved by a small amount in the vertical direction or horizontal direction. That is nothing but your A1. Even though fan is mounted rigidly, still there may be small amount of deformation. That amount, instead of saying deformation, it is a displacement. That displacement is given by A1. Suppose we want to, so instead of plastic wire, you have to mount it rigidly. Plastic wire is having very low stiffness. So finally, finite element packages will understand, so not by your these notations. Finite element packages will understand these boundary condition only when each and every boundary condition is written in the equation form. So otherwise, the finite element package will not understand. There is no standard tool like this. The ground is fixed, or fan is fixed at one end, or turbine blade is mounted on the rotor. There is no such things inside the finite element packages. All packages, whatever may be the type of boundary condition, it is explained or written in the form of the program. The program basic concept for the program is in the form of mathematical equation. So now you are writing some equations for the boundary condition. So now, so instead of going for the plastic wire, so we can mount the same fan by steel wire. Then if it is a plastic wire, deformation may be A1. If it is a steel wire, the deformation may be around, let it be 5 mm. Instead of moving the fan in the downward direction by 10 mm because steel wires are slightly stronger. So it may be moved by a small amount of 5 mm. So instead of going for a steel wire, you can rigidly mount the fan by nut and bolt system. Then deformation may be very, very small. Instead of 10 mm or 5 mm, deformation may be the displacement of that particular point. One end of the fan may be only 1 mm or zero point 0.1 mm. So that means A1 is depending upon the displacement of the node 1 is depending upon the stiffness of the plastic wire is different. So because plastic wire is having a lower stiffness, so this end can move by a large distance. This point, I mean, this is the end of the fan, this fan rod, the starting point of the fan rod. The fan rod is mounted to the roof by a plastic wire. Imagine initially you are considering a plastic wire having the stiffness K. So even though you are saying plastic, we are not saying it is a plastic in finite element package. If you say plastic, so packages will not understand. Only if you specify the stiffness K value of the plastic or Young's modulus value of the plastic. So finally required in the stiffness. So stiffness is once you know the Young's modulus, once you know the area of the cross section, once you know the length, then automatically finite element package will calculate the stiffness. You are not adding the stiffness value to the finite element packages. Either you are entering the Young's modulus, area, length of the element. So now this spring is nothing but initially it is a plastic wire having a stiffness of, let it be 5 unit. The later it is replaced by steel wire of a stiffness of 10 unit. So when stiffness is more, the movement is very less. So in the later stage, so you are mounted the same fan rod to the roof by having very high stiffness, the nut and bolt system. Then so K value is very, very high. It may be instead of 10, it may be 100 or 1000. So depending on the stiffness value, so we can get very, very small deformation, 10 mm deformation also we can get for the same end of the fan, that's the upper end of the fan, upper end of the fan rod, or we may get very, very low displacement or sometimes zero displacement. Everything is depending upon the stiffness on which your fan is coupled to the roof. Coupling, it's a coupling or mounting. In general term, it is referred to as mounting, how it is fixed to the roof. So based on that, that is physically or mechanically we are doing. So your finite element packages will understand only in terms of the stiffness. You have to express in terms of stiffness. So that's why we have one member, stiffness member, spring. It is a spring is having stiffness. When you come to the spring, the one end of the spring is moved by the distance q. This is a spring now. We have two end. This is no one end. This is the other end. The one end of the spring is moved by a distance q, a1. Other end of the spring is moved by a distance q1. If the spring stiffness is very, very high, then A1 is also equal to Q1. That is the infinite spring stiffness. But mechanically, in terms of practicality is considered, we cannot have any material having infinite stiffness. Infinite stiffness is if we apply 1000 tons of load to the spring, there is no deformation. Such type of material cannot be developed using present technology. So that is only the theoretical concept. Once you say theoretical concept, so if the stiffness of the spring is infinite, then your A1 value is also equal to Q1. That means there is no deformation. But general deformation of spring, you can say, because you are studying the spring, you studied the same spring in dynamics analysis. Also, you have two chapters. One is related to the vibration. So where you are referring, those displacements are x1 and x2. In dynamic analysis, last two modules you studied the vibration, where your displacement of node, what one end of the spring is given by x1, other end of the spring is given by x2. But in finite element analysis, same displacement is given by qa1 and q1. If the spring constant c, so normally you are using the term k, but to differentiate between the fan rod stiffness, we have the fan rod stiffness is referred by K, and how it is fan is mounted to the roof, we have either used a plastic wire or steel wire or rigid clamping system. That value of the stiffness is given by C. C is not some displacement. C is nothing but a stiffness of the mounting arrangement. In simple way, it is referred as a mounting arrangement. So because of the stiffness C, if C is very, very high value, infinite, then the fan will not move. That one fixed end of the fan will not move. When fixed end of the fan is not moved, so then A1, someone is switched on Akil. If you have any doubt, you can clarify. Otherwise, mute the audio. Akil, mute the audio. PPT is visible. Hello, PPT is visible now? Yes or no? Someone has to respond. Huh? No.
Yes, sir.
Okay, then I'll put it in because I rejoined because of some kind of problems. It is disconnected. Call get disconnected. So now, okay, is it audible?
Yes, sir.
Okay. So what
Yes,
I'm
sir.
explaining, those things are not available in most of the textbook. By knowing the knowledge of my the different subject and reading different books, I have given some simple example to understand. Those examples are not given in the textbook. Any of the textbook it is not given. Otherwise, if you start giving only equation, you don't understand it. So you should be able to understand the equations, especially in the finite element analysis or whatever may be the subject. Not only remembering the equation, you have to understand what is that equation represent. It is not just writing some diagram and writing some equation. Then it will become mathematical subject. You can teach the complete finite element subject as a mathematical subject itself. The finite element subject is there for MSc mathematics also. They'll teach like a mathematics subject. For being in mechanical engineering, you have to understand the each and every equation important. What is the behind the mechanics behind each and every equation. It is not just like the writing some equations, taking the square or differentiation, etc. Now same equation you studied in vibration. Even in your design, you are studying the spring also. The net deformation of spring is given by x2 minus x1. Here also we have the spring. We'll come to your actual problem now. So here also we have the spring. The spring is having a stiffness of C. So spring is having a stiffness C. The deformation is given by Q1 minus A1. Instead of writing x2 minus x1, you are familiar with the x2 minus x1, but instead of writing x2 minus x1, it is defined by this. So now we have strain energy in the spring. The strain energy is nothing but half into sigma into epsilon. So epsilon sigma is also converted into epsilon because sigma is nothing but E into epsilon. So E into epsilon. So epsilon, we have two epsilon. Those two epsilon become epsilon square. The strain square. So if you consider strain per unit length, then this strain energy in the spring is given by half into, it is normally kx square. So half into k is replaced by c, and x is nothing but a net deformation. The net deformation is q1 minus a1. We have general formula. Strain energy stored in the spring is nothing but half into kx square. So half into kx square. In this case, stiffness of the spring is k, and the net deformation of the spring is q1 minus a1. Now you are coming back to the original your vibration equation or equation of the spring. Now total potential energy, we have already discussed the potential energy. The potential energy term consists of one is strain energy and one more is work potential. But now we have original fan rod we have. So other than that, we introduced one more spring of having the very high stiffness C. So that means when you're talking about the strain energy, the strain energy due to the original structure with respect to fan rod, the fan rod is having some stiffness. So stiffness we can get once you know the Young's modulus area. So stiffness is nothing but AE by L, that gives the stiffness of the fan rod. That is the original structure stiffness. Plus we have another spring is added or mounting arrangement. I have given the wire of steel wire or plastic wire, or it's rigidly mounted using nut and bolt system, etc. Then we have the strain energy, or some amount of strain energy is also stored on those component. That is nothing but strain energy due to original structure. So there is original structure is fan rod, and other structure is strain energy due to the additional spring. That is nothing but a C. Additional springs is nothing but your clamp mounting arrangement. Plus work potential is there. Work potential I am not shown here. So now the strain energy due to the original structure is given by half into Q transpose K into Q. That is nothing but half into, we have original equation. This equation we have. So strain energy stored in the body is repeatedly, I am showing this diagram. The complete finite element analysis based on your simple stress strain curve. So where energy stored in the body is nothing but area of the stress strain curve. So area of the stress strain curve is nothing but half into base into height. Base is epsilon, height is sigma. So finally this sigma can be written into E into epsilon. So E into epsilon you can write as like this, half into E into epsilon into E in this form. Then we can write as half into epsilon transpose E into epsilon. So epsilon is nothing but strain, that is nothing but strain. The strain per unit length is nothing but Q. The Q is nothing but a strain per unit length. If you consider unit length, we have the total strain. So general formula for a strain is delta L by L. So if the length is 1 unit, so then the strain is nothing but delta L itself. The strain per unit length is nothing but a delta L. So delta L is nothing but a deformation. So deformation is nothing but a Q here. So we have half into epsilon T E into epsilon. That also can be written in this form. That is strain energy due to original structure is half into Q transpose K into Q. That is the strain energy. Q is the displacement vector. In finite element analysis, this is the equation in simple way. This is the mechanics of material equation for the strain energy. So equivalent equation in finite element analysis is half into Q transpose Q into Q. That is the equivalent equation in the finite element analysis, where Q refers to the strain per unit length, and this is also Q, strain per unit length, or Q is your displacement vector. It's a transpose of the displacement vector. So now we have the strain energy for the element, this steel rod, this first term, and second term is the strain energy for the addition structure. Addition structure is, I am given the example of plastic wire or steel wire or mounting arrangement. That is the addition structure. So strain energy is given by, for the spring is given by half into Kx square. That already you have defined. So K is nothing but the stiffness of the mounting arrangement. That is nothing but C. And X square is nothing but a net deformation of the mounting arrangement or a additional springs. So that is nothing but Q1 minus A1. That is nothing but already you have seen that part. So net deformation of the spring is Q1 minus A1. The stiffness of the spring is C. So this is the strain energy for the additional structure, additional spring, and work potential is nothing but your force into distance. So now we have the same equation already we have defined for the bar. Already we have defined the equation for the bar element, the potential energy. Now you have to differentiate this equation, differentiate this potential energy functional with respect to Q1 as well as A1. So now, so one is differentiation of this equation with respect to Qi is equal to 0. That means, so in the case of bar element you have seen, that's why I started with the bar element. This is a differential equation for the bar element. You have to differentiate this equation with respect to U1 as well as U2. Those are the displacement component. In the similar way, we have strain energy for the total. We have the strain energy, total strain energy. This is the total strain energy equation. Then you have to differentiate this equation with respect to Q1, Q2, Q3, etc. We'll get n number of equation, but I was not worried about all how many n number of equation. But as per this topic is considered, you have to understand what is the equation for potential energy. The potential energy is nothing but strain energy plus work potential. The work potential is equal to nothing but work done, that's equal to force into distance. And the strain energy in terms of in FEM is, in mechanics of materials, strain energy is given by half into epsilon transpose E into epsilon. But the same equation you can write in the finite element analysis as Q transpose K into Q. So that those are the fundamentals you have to remember. But you are mounted, we have bar, end of the bar is mounted by rigid spring of having stiffness C. Imagine you have mounted this, imagine this is a fan rod, this is the actual structure fan rod. This fan rod is rigidly mounted with mounting nut and bolt system. It is having the stiffness of C. Now we have a potential energy function exactly similar to bar problems. You have to differentiate with respect to Q1, Q2, Q3, etc. We will get n number of equation. So now we are familiar. Now you can understand. Already you have dealt with KQ is equal to F equation. So we are getting KQ is equal to F equation by applying potential energy function. Already we have derived, you are found out K1, K2, K3, etc. From that, so you are getting the potential stiffness matrices KQ is equal to F. So same stiffness matrix you are getting by applying potential energy functional. I think if you know that part, it is okay. Now I'll stop, and tomorrow once again I'll continue. If you know those, if you understand this concept, how to apply. Finally, you have to remember in terms of equation, final equation. Like I have some practical example also. So when one end of the bar is fixed, what is the displacement, or what is the final equilibrium equation? When another end of the bar is fixed, that is the application part. If you know that understand this example, that is also sufficient for heat transfer analysis of the problem is considered like that. So I'll stop here, and we'll continue tomorrow. So that is part of your the heat finite element analysis of the heat transfer. As per your assignment is given, first you finish only the assignment 3. Assignment 2 I'll give some more time because I don't want to mix. So you have to understand, you have to write, not writing by waiting till last day and writing in the last day in the up to 1 o'clock, 2 o'clock and finishing. That I don't want such type of submission of assignment. I have given sufficient time for assignment. You have to understand, you practice, then you write it in the assignment book or sheet, then scan it and upload to Google Classroom. Don't write assignment for just sake of submission of the assignment. If you do it like this, it is wastage of time for you also. It is a wastage of time for me also, just simply checking all the assignment. Don't do, it will not helpful for you also, it will not helpful for me also. So you may get some mark for assignment, that is a different issue. But purpose of giving assignment is, so instead of studying in the last moment, so you can study during the, after finishing of each chapter. If you write some assignment, so you can understand better. You know, if you have any difficulties also, you can clarify with your friends or with me. That's the purpose of giving the assignment. So tomorrow is the last date to submit assignment 3, that is beams and torsion problems. So other assignment 2, I'll give another 1 week time. Most probably this weekend or Monday, maybe next Monday is the submission date for assignment 2. I may add 1 or 2 problems. Don't worry about number of problems, number of questions, etc. So you write the assignment, understand and practice. It is nothing but a additional practice for you. So okay, I'll stop, and tomorrow I'll continue. So don't worry about this complete, understand this complete potential energy concept. How to apply potential energy function for applying boundary condition, that is sufficient for heat transfer problem is considered.